All right, this video is part two of the Atwoods series. So in the first video, we looked at the first type of Atwoods machine, which was something that looked like that, if you remember the work. So the pulley was just attached to the ceiling, and you just had two masses going up and down. In this situation, we are now going to be looking at a situation where one of the blocks is on a tabletop, a horizontal tabletop, and one of the blocks is hanging over the edge. So basically what that means is now we are dealing with not only blocks that are moving in different directions, but we have blocks that are moving in different directions in different axes. So we've got the one block, the 8 kilograms, that's going up and down. And so notice on the left I've designated the up, the positive direction. But we also have the 4 kilogram block that's moving left and right. And so we need to have a positive direction for horizontal as well. And I usually stick with the math way of doing it, which makes everything up and to the right positive. So if we're dealing with any motion or any sort of vectors in the horizontal direction, the right is going to be designated positive. And if we're dealing with any vectors that are going in the vertical direction, up is going to be positive. Okay, so the question is, what is the acceleration of the 8 kilogram block, and what is the tension in the string? Remember, we are using frictionless pulleys and massless pulleys and strings. And for this first problem, we're going to make it simple. And we are going to assume that the surface exerts no friction on the 4 kilograms. So we're dealing with a frictionless tabletop. And then what we are going to do is look at an example in the next screen that deals with friction. All right, so let's look at what's going on here. So if I drew a force diagram for the 4 kilogram block, what that would look like is I'd have force gravity going down, I'd have force normal going up, and I'd have force tension that's pulling to the left, excuse me, to the right. And there's no friction, so that's it. That's all the forces that are acting on the 4 kilograms. And then what I'm going to do is I'm going to draw a force diagram for the 8 kilogram. The 8 kilogram block has force gravity going down, and it has force tension going up. And what I should probably do, because it'll be important, what I'll probably do is I'm going to put a little sub 4 here and a little sub 8 there, because I want to know that those gravities are different. So if I see FG, what FG am I talking about? Okay, now you can still take the system off the off the pulley, just like we did before. So if we did that, let's actually draw that out. So if I took the system off the pulley, what it would look like is it would look like here's my 4 kilogram block. There's attached to the string. Okay, there's the 8 kilogram block. All right, and then let's draw those forces in there. So the 4 kilograms still has the gravity pointing down and the normal pointing up, because we didn't have to turn or change that direction, right? We only had to change the 8 kilogram one. So the 4 kilograms still has the normal going up, the gravity going down. Tension is going to the right. 8 kilograms tension will now go to the left because of the way we've moved it. And then that gravity is now pulling off to the side. And that's the 80 newtons there. So when we look at it like that, what's the force net coming from? Well, the normal and the gravity are canceling each other out. Those are gone. These two tensions cancel each other out. So really the force net that's acting on the system really just comes from the force gravity from the 8 kilogram block. And so that's what we're going to do. We're going to set that equal to mass times acceleration. So the force gravity from the 8 kilogram block is the 80 newtons equal to the mass of the system. 8 plus 4 is 12 kilograms times A. And then to get my acceleration, I just do 80 divided by 12, and I get my acceleration is 6.67 meters per second squared. And then I just have to check and see, okay, what am I asked to solve? What is it asking the acceleration for? And it's asking for the 4 kilogram block. And so the 4 kilogram block is going to accelerate to the right, and notice I've made to the right positive. So my answer is a positive 6.67 meters per second squared acceleration. Now what I'm going to do is I'm going to go ahead and solve for the second part, and that is what is the force tension that is experienced between the strings. And just like before, nothing's changed. We are going to pick one of the blocks. It doesn't matter which block you choose. Let's go ahead and choose the 4 kilogram block, since that's what it's asking for. It's asking for the 4. Okay, so I draw my force diagram again for the 4 kilogram block. It's force gravity going down, force normal going up, and then force tension is moving to the right. So when I think about force net acting on the 4 kilogram block, what force is contributing to the net force? Well, normal and gravity, they don't because they cancel each other out. It's an equilibrium in the y. So really it's just force tension that's contributing to the net force. And that's perfect because that's actually what we're going to solve for. So we don't have to worry about subtracting any vectors or anything like that for the force. There's just one. So force tension is going to just be equal to the mass, which is 4 kilograms, times its acceleration. We know its acceleration is positive. So 6.67 times 4 kilograms is going to give me a force tension of approximately 26.67 newtons. And notice it's positive, which makes sense because the force tension is pointing in the positive direction. All right, now let's go ahead and do one where we have friction. Okay, so let's look at this example. We have a 5 kilogram block on the tabletop, 7 kilogram block is hanging over the side. Up is positive, and I'm still going to make to the right positive. All right, I want to know what's the acceleration of the 7 kilogram block and what is the tension in the string. And like I said, we are going to make friction in this problem. So our coefficient of kinetic friction, since it's moving, let's make it 0.12. Okay, I'm just making this up right now, but we'll say it's 0.12. Okay, so first of all, we need to figure out what is the acceleration. So step one, acceleration. And so I'm going to draw my force diagram. We've got force gravity here, force normal here. Let me write those values in there. Force gravity is 50 newtons. Force gravity is 50 newtons. Force normal is 50 newtons. I've got tension that way, which is I'm going to have to solve for that one. And I do have force friction this way as well. And I'll go back and solve for that one. For the 7 kilogram, I've got force gravity down. That's going to be 70 newtons. I've got force tension up, but I don't know what that is. But I do know it's equal to that force tension as well. Okay, so we have everything solved for except for force tension, which is what we'll do in the second part. But force friction, we need to figure out what that is. What is the friction force that it would be experiencing? Well, the friction force is going to be the mu times the force normal. And so that's 0.12 times the normal, which is 50, because the friction's acting on the 5 kilogram block. It's not acting on the whole thing, because 7 kilograms doesn't experience friction. It's not on a surface. Okay, so it's just going to come from the 5 kilogram, and so 0.12 times 50 gives us a frictional force of 6 newtons of frictional force. And so I'm going to write that up in my force diagram. Force friction is 6 newtons. Okay, so then just like before, let's figure out what is the net force. What force are contributing to the net force? Well, normal cancels out with gravity there, and this tension cancels out with the tension from the 7 kilogram. So really, the only forces that are contributing to the net is the force gravity from the 7 kilogram box, and then the force friction from the 5 kilogram box. And ask yourself right now, are those forces helping each other, or are they hindering each other? And hopefully you can see that the forces are hindering each other. They are not working together. They are taking away from each other. And so what that means is when we go to write my force net, we're going to take those two forces and subtract them. So you've got the 70 newtons right here that wants to pull it down, but 6 newtons is acting against it. And so what that means is my force net is just 64 newtons. It's 70 minus 6. That's equal to the mass of the whole system, which is 12 kilograms, times my acceleration, which is what I'm solving for. So my acceleration is just 64 divided by 12, or 5.33 meters per second squared. And then I need to figure out what's it asking for? Is this the acceleration of the 5 or the 7? And it's for the 7 kilogram block. And the 7 kilogram block accelerates down. And down is negative according to my reference over here to the left. So that's actually a negative 5.33 meters per second squared. Okay, now let's go ahead and solve for the force tension. I'm going to use the 7 kilogram block because that's what it's asking for. But remember, it doesn't matter. You'll get the same answer for force tension whether you use the 5 or the 7. So on the 7 kilogram block, it's got force gravity going down of 70 newtons. And force tension is going up. We don't know what that is. We're going to solve for that. All right, so my force, let me see if I can move this up out of the way a little bit. There we go. Give myself a little bit more space. So my force net equals mass times acceleration. Remember, now I'm only focused on the 7 kilogram block. That's going to be the force tension plus force gravity, because those are the two forces acting on it, is equal to mass times acceleration. Force tension is what I want to solve for, plus gravity. Well, gravity's 70, but it's negative 70. That's equal to the mass, which is 7 kilograms, times the acceleration is 5.33, but it's accelerating downwards, and down is negative, so I need to make sure I put in negative 5.33 meters per second squared. I clean that up a little bit. I get force tension here, minus 70 equals 7 times negative 5.33 gives me negative 37.33 newtons. And then so I add 70 to both sides, and I end up getting that my force tension is equal to 32.67 newtons. And this concludes the video on the second part of the Atwoods machine series.